right, now to determine what element we're looking at, basically you just want to concentrate on the very last thing in the configuration. So this 4s1 should tell us exactly what we need. All right, so when you look on the periodic table, 4s1 ends at the element K or potassium. Okay, the next element is 43, so you look on your periodic table at 43. Remember the D's are off by 1, so it's really the fifth row, but that's the 4D, and 43 is going to be the element NB. Okay, all right, the next one's a noble gas configuration, but still you're going to be looking at the N, so 48, so krypton, and then 48, that would be PD, palladium. All right, and then last we have 3P1, and 3P1 is going to be aluminum. Okay. All right, this one wants us to fix any mistakes in the configuration. So basically you just want to go along and find any mistakes. So we got 1s2, 2s2, 2p6, 3s2, 3p8, well that's weird, should be 6, 3p6, 4s2, 3d10, 4p6, 5s2, 4d3. Okay, so everything else looked good. All right, the next one is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, should be 3d10, 4p6, 5s2, and then that should be 4d3. Okay? All right. Copper, we think, would have the electron configuration 4s2, 3d9, but actually it has 4s1, 3d10. Why does this happen? Well, it has to do with that D sublevel. That D level has 5 orbitals in it, and when you have 9 electrons, they fill it like so. So you have one empty space. So if it just pulls that one from the S and gives it to that 3D, then we have a full orbital. Full orbitals equal very stable. Okay, other elements that follow this exception are going to be right under copper, so silver and gold. All right, what other exceptions occur in the d orbitals? Well, if you have a element that is, say, 4s2, 3d4, this would be chromium, so argon. All right, there's the noble gas. All right, it will do the same thing. So you got your d orbital, and then you got your little 5 boxes, and you would get 1 up, 1 up, 1 up, 1 up. Okay, so you would be missing 1. So if you took that 1 from the S and gave it to the 3D, you'd then be at 4s1, 3d5. Okay, so half full is the next best way to be stable. So it's like the second best stable. Okay, and other elements that follow this rule are going to be those below chromium, so Mo and tungsten. Okay, all right, on this chart, we're trying to figure out the charge. We're going to get the charge from 1 plus 2 plus 3 plus skip, 3 minus 2 minus 1 minus zip. So bromine would be 1 minus, francium would be 1 plus. It told us lanthanide is 1 plus, or lanthium, and then TL is 3 plus. Okay, so this one had to have gained an electron to become negative. This one lost an electron. Again, we lost an electron. And then here we lost 3 electrons. All right, the next step wants you to go back to the previous configurations you had and fix them. Okay? Well, of course, my computer went down, so everything crashed. But you basically need to go back for the electron configuration. And your electron configuration says that you should gain 1 electron. Well, you ended on 4p5. So you should fix your electron configuration to read 4p6. The end of your noble gas configuration should read 4p6. Your orbital diagram in your 4p, you would have had one empty spot. So you would go ahead, oops, wrong way, got to be spin down. You go ahead and spin that one down. And then in your Bohr model, you would add one electron to the outside ring. Okay, francium is the opposite. You lose an electron. So francium ended up in 7s1. So basically 7s1 goes away in the electron configuration and the noble gas. In the orbital diagram, you would have had 7s with an up arrow. Well, it goes completely away. And then for your Bohr diagram, you just take off one electron on the outside ring. All right, lanthanum, same thing. Lanthanum would have ended up on, you would have either had 4F1 or you would have had 5D1. Okay, so this was the one you could have chose. So whichever one you chose, you would cross out for the electron and the noble gas. Whichever one you chose for the orbital diagram, that complete orbital gets crossed out. And for the Bohr diagram, you just take one off the outside ring. All right, and then thallium, he loses 3. So you should have ended up with, let's see, he would have been, let's see, 6s2, 4f14, 5d10, and then 6p1. Well, you would lose from the outside ring, so you really should lose the 6s2 and 6p1, you would think. Okay, because they're the outside rings. But if you'd taken 2 from that D, I think I would have accepted that too. Noble gas should just match whatever you did. The orbital diagram, you're going to cross out the 6p box, and then whichever one you decided to take some from, you would have to cross out 2 in those as well. The Bohr diagram, you just eliminate 3 electrons from the outside ring. All right, and the last section, explain, explain, explain. All right, when you're talking about a metal halide in a flame, you're talking like copper chloride, something like that. Okay, so basically what happens is you put it in the flame, energy goes in and is absorbed by the electron, and the electron jumps up. Okay, so energy added and electron absorbs that energy, absorbs energy, and jumps up to higher ring. Okay, and then over here, that same electron will jump back down, and when it does, it will let off energy in the form of light. Okay, so electron jumps back down and emits energy in the form of light. All right, emission spectrum, you would see a full rainbow spectrum here, and then you would have certain little black lines wherever the electrons were absorbing that energy, okay? So that would be absorption spectra. So that's this one, okay? So that's this one right here. Absorption spectra, okay? So it relates to the absorption when the energy is absorbed. Emission spectra is the opposite. Emission spectra is like a black background, and then you have a couple of colored lines indicating the energy that is given off, the wavelength of light that's given off whenever that electron jumps back down and gives off the energy in the form of light, okay? So emissions, when it's emitted, absorption is when it is absorbed. They satisfy law of conservation of energy because these wavelengths are the exact same. So the ones that are missing here are the ones that are present there. Okay? All right, larger atoms tend to have more complicated spectral lines because They have more electrons, therefore there are more transitions available. And the quantum mechanical model basically talks about electrons as waves, and it's a very complicated mathematical model.